4.5 billion years. This number is so enormous that the human mind is simply incapable of comprehending it. If the entire history of Earth were compressed into a single day, then all of human civilization would occupy the last 4 seconds before midnight. Everything we know, everything we have built, all our wars and discoveries, love and hatred, births and deaths, for seconds. But what happened during the remaining 23 hours, 59 minutes, and 56 seconds? We're going to a place where no human foot has ever stepped. Not because it is far away, but because it was unimaginably long ago. We will travel through the abyss of time, and what we will see will change our understanding of what it means to be part of this planet. Let us begin at the moment when Earth did not yet exist. About 4.6 billion years ago, in one of the spiral arms of the Milky Way galaxy, a giant cloud of gas and dust was rotating. This cloud was the remnant of exploded stars, supernovae that, at the moment of their death, created all the heavy elements that would later form our planet. The iron in your blood, the calcium in your bones, the carbon in every cell of your body. All of this was forged in the hearts of dying stars billions of years ago. Something disturbed this cloud, perhaps a shock wave from a nearby supernova or the gravitational influence of a passing star. The cloud began to contract, slowly, very slowly by human standards, yet inexorably. Temperature and pressure in the center rose. Gas particles collided more and more frequently, accelerating to incredible speeds. And one day, when the temperature reached 10 million degrees, a miracle occurred. Hydrogen atoms began fusing into helium, releasing colossal amounts of energy. The sun was born, but around the young star, a disk of gas and dust still rotated. And within this disk, processes unfolded that would lead to the formation of our home. Tiny dust particles collided and stuck together. At first, they were the size of grains of sand, then peas, then stones. This process is called accretion, and it continued for millions of years. Gradually, larger bodies, planetesimals, began to form in the protoplanetary disk. They were the size of asteroids several kilometers across. Their numbers grew, and they collided with one another. Some collisions were destructive, bodies shattered into fragments, but others led to merging, forming ever larger objects. About 4.5 billion years ago, in the region where Earth's orbit is now, one of these objects became massive enough for its gravity to begin actively pulling in surrounding material. This was Proto-Earth, the embryo of our planet. It was incandescent, covered by an ocean of magma, constantly bombarded by asteroids and comets. There was nothing on its surface we would recognize. No continents, no oceans, no atmosphere in the modern sense. Only molten rocks stretching to the horizon, and a sky filled with smoke and steam. But the most dramatic event in the history of young Earth was still ahead. About 4.47 billion years ago, there existed another planet in the solar system. Scientists call it Theia, after the ancient Greek goddess, mother of Selene, the goddess of the moon. Theia was roughly the size of Mars and moved along an orbit that was destined to intersect Earth's. And they collided. Try to grasp the scale of this catastrophe. Two worlds, each the size of a planet, slammed into each other at a speed of about 40,000 kilometers per hour. The energy of this impact was so enormous that both planets were almost completely melted. Theia was destroyed. Most of its mass merged with Earth, but a huge amount of debris was ejected into orbit. These fragments gradually came together and formed the moon. So when you look at the moon in the night sky, remember, you're looking at a scar left by the greatest catastrophe in the history of our planet. But this catastrophe turned out to be a blessing. The moon stabilized Earth's axis of rotation, created tides that would later play a crucial role in the evolution of life. And perhaps the very collision with Theia gave Earth extra heat and material necessary to form its unique characteristics. After the collision with Theia, Earth was a true hell. Its entire surface was covered by an ocean of magma hundreds of kilometers deep. The surface temperature reached several thousand degrees. The atmosphere consisted of incandescent vapors of rock glowing with a dim red light. If an observer had existed, watching Earth from space at that moment, they would have seen not a blue planet, but a crimson sphere resembling a dying ember. But time passed, and Earth began to cool. This happened very slowly, over millions of years. The surface of the magma ocean gradually solidified, forming the first crust. But this crust was unstable. It was constantly destroyed by eruptions from the depths and by falling asteroids. Earth at that time resembled a boiling cauldron, on the surface of which crust formed and broke again and again. Water vapor, which made up much of the early atmosphere, began to condense as the planet cooled. And one day, when the temperature dropped below the boiling point of water, it began to rain. But this was no ordinary rain. It was rain that lasted millions of years. Water fell onto the molten surface, evaporated instantly, rose, cooled, and fell again. This cycle repeated countless times until the surface finally cooled enough for water to remain liquid. Thus, the first oceans appeared. They were unlike modern ones. Their water was acidic and saturated with dissolved minerals. Its color was likely greenish or brownish due to the high content of iron and other metals. These oceans covered almost the entire planet because the first crust was thin and lay below water level. Only here and their volcanic islands rose above the surface, spewing lava and ash. The atmosphere of early Earth contained no oxygen. It consisted mainly of carbon dioxide, nitrogen, water vapor, methane, and ammonia. The sky was not blue, but orange or reddish. The sun shone about 30% dimmer than today, but the greenhouse effect from the high concentration of carbon dioxide maintained temperatures high enough for liquid water to exist. We enter the period geologists call the Hadean, named after Hades, the ancient Greek god of the underworld. This was an era of endless catastrophes. Asteroids and comets continued to bombard the young planet. Some impacts were so powerful that they could vaporize entire oceans. But water returned, partly from the atmosphere, partly delivered by new comets. And it was in this chaos, in this hell of molten rock, poisonous atmosphere, and constant cataclysms, that something incredible happened. Something scientists still cannot fully explain. Among dead matter, the first living cell appeared. How did this happen? This is one of the greatest questions of science. We know that life appeared on Earth very early, perhaps as early as 4 billion years ago, when the planet had barely cooled after its formation. This means that either life arises relatively easily under suitable conditions, or we were incredibly lucky. There are several theories about the origin of life. One of the most popular involves hydrothermal vents at the bottom of the ocean. These underwater volcanoes release hot water rich in minerals and chemical compounds. At the boundary between the hot water and the cold ocean, a gradient of temperature and chemical composition is created, which could serve as an energy source for the first primitive forms of life. Another theory suggests that so-called black smokers, hydrothermal vents releasing metal sulfides, played a key role. These minerals could act as catalysts for chemical reactions leading to the formation of the first organic molecules. There are also more exotic hypotheses. According to the panspermia theory, life may have been brought to Earth from space, on comets or meteorites. We know that organic molecules, including amino acids, the building blocks of proteins, have been found in meteorites and in interstellar space. Perhaps the seeds of life travel across the universe, sprouting wherever they find suitable conditions. But whatever the exact sequence of events was, the result is known to us. About 4 billion years ago, the first living organisms appeared on Earth. They were incredibly primitive compared even to modern bacteria. Most likely, they were simple RNA molecules capable of copying themselves. RNA is a relative of DNA, but simpler and less stable. According to the RNA world hypothesis, the first forms of life were based on RNA, which served both as a carrier of genetic information and as a catalyst for chemical reactions. These first replicators lived in the ancient ocean, using dissolved chemical compounds for energy. They did not photosynthesize, did not breathe oxygen. There was none in the atmosphere. They existed in complete darkness of the ocean depths or in hot vents, feeding on the energy of chemical reactions. And they evolved, slowly, randomly, without any goal or direction. Random errors during copying created variations. Some variations proved more successful at surviving and reproducing. They were passed on to the next generations. Others were unsuccessful, and their carriers died without leaving offspring. This was natural selection, a blind mechanism capable nevertheless of creating structures of incredible complexity. At some point, we don't know exactly when an important transition occurred. The first true cells appeared, with a membrane separating their internal contents from the external environment. This was a tremendous step forward. The membrane allowed the cell to control which substances entered and which left. It created a protected space where complex chemical reactions could take place. These first cells were prokaryotes, organisms without a cell nucleus. Their DNA floated freely inside the cell, not enclosed in a separate compartment. Modern bacteria and archaea are the descendants of those ancient prokaryotes, and they remain the most numerous and diverse forms of life on Earth. About 3.5 billion years ago, a revolution took place that forever changed our planet. Some bacteria learned how to photosynthesize, to use the energy of sunlight to produce organic molecules from carbon dioxide and water. This process had one important byproduct: oxygen. The first photosynthesizing organisms, cyanobacteria, were unimpressive in appearance. They formed thin films on rocks and on the surface of the water, but their impact on the planet was enormous. They began to fill the atmosphere with oxygen, but this process was not fast. Oxygen is a highly reactive gas. As soon as it entered the atmosphere, it immediately reacted with other substances. It oxidized the dissolved iron in the oceans, which settled to the seafloor as rusty sediments. These sediments are mined today as iron ore, banded iron formations that are direct evidence of ancient cyanobacteria. Billions of tons of iron had to be oxidized before oxygen could begin to accumulate in the atmosphere. This process took about 2 billion years. Only around 2.5 billion years ago did the oxygen concentration begin to increase significantly. This event is known as the Great Oxygenation Event, or the oxygen catastrophe. Why a catastrophe? Because for most living organisms of that time, oxygen was a deadly poison. They had evolved in an oxygen-free world and had no protection from its destructive effects. When the atmosphere filled with oxygen, a mass extinction occurred. Most species of anaerobic organisms died out or were pushed into the few places where oxygen did not penetrate: deep soil layers, seafloor sediments, the intestines of animals. But some organisms learned not only to tolerate oxygen, but to use it. Aerobic respiration turned out to be an incredibly efficient way to obtain energy, about 18 times more efficient than anaerobic processes. Organisms that mastered this method gained a huge advantage. They could grow faster, move more actively, and occupy new ecological niches. Oxygen changed not only the biosphere, but the planet itself. It reacted with methane, a powerful greenhouse gas that had previously kept Earth warm. Methane levels dropped sharply, and the planet began to cool. Around 2.5 billion years ago, one of the most extreme glaciations in Earth's history began, the Huronian glaciation. Glaciers covered vast territories, perhaps reaching the equator. Some scientists believe that at certain times the Earth may have become a snowball, a planet completely covered with ice. This hypothesis, known as Snowball Earth, remains debated, but there is no doubt that the climate of that time was extremely cold. How did life survive these glaciations? It likely persisted in a few refuges, around volcanic heat sources, beneath the ice of the oceans where the water remained liquid, and in other shelter environments. Life demonstrated remarkable resilience in the face of catastrophe, a quality it would show again and again throughout its history. After the end of the Huronian glaciation came a long period of relative stability. It is sometimes called the Boring Billion, a stretch of time from about 1.8 billion to 800 million years ago when it seemed nothing particularly special happened on the planet. Continents drifted slowly, oceans swayed, bacteria multiplied in their microbial mats. Life existed, but did not develop into more complex forms. Yet even during this period, important events took place. Around 2 billion years ago, the first eukaryotes appeared, cells with a true nucleus enclosed by a membrane. This was a revolutionary step whose significance is hard to overestimate. How did eukaryotes arise? According to the endosymbiotic theory proposed by Lynn Margulis, they originated from the merging of different prokaryotic organisms. An ancient archaean engulfed a bacterium but did not digest it. Instead, the bacterium began living inside its host, providing it with energy in exchange for protection and nutrients. This bacterium became the mitochondrion, the organelle that produces energy in all eukaryotic cells, including ours. Later, a similar process happened again. Some eukaryotes engulfed cyanobacteria, which became chloroplasts, the organelles responsible for photosynthesis. Thus, the ancestors of plants and algae appeared. The evidence for this theory is numerous and convincing. Mitochondria and chloroplasts have their own DNA, different from the DNA in the cell nucleus. They reproduce by division, like bacteria. Their membranes have a structure characteristic of bacterial membranes. All of this points to their origin from free-living bacteria. The appearance of eukaryotes opened the path to multicellularity. Single-celled eukaryotes were larger and more complex than prokaryotes, but the real evolutionary leap occurred when they learned to form colonies and then true multicellular organisms. The first multicellular beings were simple. They may have resembled modern slime molds or primitive algae. But over time, the cells within these organisms began to specialize. Some cells were responsible for nutrition, others for reproduction, others for protection. This division of labor made it possible to create structures of complexity impossible for single-celled organisms. Around 800 million years ago, the Boring Billion ended. A new era of upheaval and change began. The supercontinent Rodinia, which had united most of Earth's land, started to break apart. This triggered intense volcanism and changes in oceanic and atmospheric circulation. And again, glaciation returned, this time even more severe than the Huronian. This was the Cryogenian period, a time when Earth may indeed have become a snowball. Glaciers covered the entire surface of the planet, from the poles to the equator. Oceans froze to depths of up to a kilometer. Temperatures fell to -50 degrees, even in the tropics. It seemed that life on the planet was doomed. But life survived. It persisted around volcanoes breaking through the ice. It existed in the thin layer of liquid water beneath the ice, where sunlight could not penetrate, but where enough heat from Earth's interior remained. It clung to existence in the harshest conditions, and it prevailed. How did the glaciation end? Volcanoes continued to erupt, releasing carbon dioxide into the atmosphere. Normally, this gas is absorbed by the oceans and bound into rocks through weathering. But when the entire planet was covered with ice, these processes nearly stopped. Carbon dioxide accumulated in the atmosphere, creating an increasingly powerful greenhouse effect. Eventually, the temperature rose enough to begin melting the ice. And once this started, the process became runaway. Dark water and exposed land absorbed more heat than the reflective white ice, accelerating the melting. In just a few thousand years, the planet shifted from global glaciation to extreme warming. The result of these cataclysms was a true evolutionary explosion. After the end of the Cryogenian, around 630 million years ago, the first complex multicellular organisms visible to the naked eye appeared. This was the Ediacaran biota, strange creatures unlike anything in the modern world. Ediacaran organisms had no skeletons, shells, or other hard parts. They were soft-bodied, and we know them only from the imprints preserved in ancient rocks. Some resembled leaves or feathers attached motionlessly to the seafloor. Others looked like quilted mattresses or inflated cushions. Still others had the shape of discs or three-rayed stars. Scientists still debate what these creatures actually were. Were they animals, plants, or something entirely different? A separate kingdom of life that left no descendants? Perhaps we will never know the answer. The Ediacaran biota disappeared about 540 million years ago, replaced by an entirely new world. This new world arose as a result of an event that paleontologists call the Cambrian explosion. Over a geologically short period, only a few tens of millions of years, most of the major animal groups that exist today appeared. Arthropods, mollusks, chordates, echinoderms, all of them originated in the Cambrian period. What caused this explosion of diversity? Many hypotheses exist. One of them links it to the rising concentration of oxygen in the atmosphere and oceans. Oxygen is necessary for the intense metabolism of large, active animals. Once enough of it accumulated, evolution gained the opportunity to experiment with new forms of life. Another hypothesis points to the emergence of predation as the driving force of evolution. Before the Cambrian explosion, most organisms were filter feeders or consumed organic particles on the seafloor. When the first predators appeared, their prey came under selective pressure to develop defensive adaptations, shells, armor, spines. Predators, in turn, evolved more effective means of attack. An evolutionary arms race began, and it continues to this day. Another important innovation of the Cambrian was the appearance of eyes. The first true eyes evolved in trilobites, marine arthropods that were among the most successful animals of their time. Eyes made it possible to actively search for prey, detect predators, and navigate the environment. They provided such an advantage that they quickly spread across different animal groups. The Cambrian seas would have been an astonishing sight to a modern observer. They teemed with life, but almost all of these creatures would have seemed strange and unfamiliar to us. Arthropods dominated, trilobites of all sizes, from tiny ones the size of a fingernail to giants half a meter long. Strange, soft-bodied creatures resembling feathered fans. Animals that looked like walking cacti or porcupines. Anomalocaris, the largest predator of its time, reaching a meter in length, with two jointed appendages and a circular mouth lined with teeth. Yet among all this diversity lived a modest creature destined to give rise to all vertebrate animals, including us. This was Pikaia, a small worm-like organism about 5 centimeters long. Pikaia had a notochord, a flexible rod running along its back, the predecessor of the vertebral column. It swam by bending its body from side to side. Nothing hinted that the descendants of this unremarkable organism would one day walk on land, rise into the sky, and even leave their planet. The Cambrian period ended about 485 million years ago, but evolution did not stop. The next 100 million years, the Ordovician and Silurian periods, were a time of further diversification of marine life. The first fish with true jaws appeared. Corals developed, building huge reefs. The seas filled with cephalopods, nautiloids whose shells reached several meters in length. But the most important event of these periods happened not in the sea, but on land. About 470 million years ago, the first plants ventured onto land. Until that moment, land was a dead desert. Bare rocks, sand, and stones washed by rain and wind. No soil in the modern sense, only mineral debris. No life except, perhaps, thin bacterial films on wet surfaces. The move to land was a colossal challenge. Plants had to solve numerous problems. How not to dry out without surrounding water, how to obtain nutrients from poor substrate, how to reproduce without water to transport spores or gametes. The first land plants were primitive. They had no roots, leaves, or stems in a modern sense. They resembled green mats spreading across moist surfaces near bodies of water. But gradually, they evolved, developing increasingly advanced adaptations to terrestrial life. The appearance of plants on land transformed the planet. Plants began breaking down bedrock, contributing to soil formation. They slowed erosion, stabilizing the surface. They added oxygen to the atmosphere and removed carbon dioxide from it. Land, once a lifeless desert, began to turn into a place suitable for life. Animals followed plants on a land. The first were arthropods, ancestors of modern insects, spiders, and millipedes. They fed on plants and decaying organic matter. Some became predators, hunting their plant-eating relatives. About 380 million years ago, another historic event occurred. The first vertebrates moved onto land. These were descendants of lobe-finned fish, whose fleshy fins gradually evolved into limbs capable of supporting the body outside water. The first tetrapods were amphibians, dependent on water for reproduction. But they opened the way for their descendants, who would eventually fully conquer the land. The Devonian period, during which vertebrates first emerged onto land, is sometimes called the Age of Fishes. And rightly so. Fish in the oceans reached unprecedented diversity. Huge armored fish, the placoderms, were the top predators of their time. Dunkleosteus, the largest of them, reached 10 meters in length and had jaws capable of biting a shark in half. The first true sharks appeared in the Devonian and began their long journey toward dominance, which continues for hundreds of millions of years. But the Devonian ended in catastrophe. About 360 million years ago, one of the largest mass extinctions in Earth's history occurred. Up to 75% of species disappeared. Shallow tropical seas were hit especially hard. Corals, stromatoporoids, and many groups of fish. The causes of this extinction remain unclear. Perhaps global cooling played a role, caused by the spread of land plants, which drew carbon dioxide from the atmosphere. Perhaps volcanic eruptions or asteroid impacts were to blame. Whatever the cause, life on Earth was pushed back but not annihilated. It recovered and continued to evolve. The next period, the Carboniferous, became a time of flourishing terrestrial life. The climate was warm and humid. The atmosphere contained far more oxygen than today, possibly up to 35% compared to the current 21. This allowed insects to reach gigantic sizes. Dragonflies with wingspans of up to 70 centimeters flew over the swamps. Millipedes more than 2 meters long crawled among the ferns. And the ferns of that era were not the modest plants we know today. Tree-like ferns, horsetails, and lycopsids grew 30 to 40 meters tall, forming dense, dark forests. These forests covered swampy lowlands spanning thousands of kilometers. When trees fell into swamp water, they did not fully decompose. Bacteria had not yet evolved the ability to efficiently break down wood. Layer by layer, organic matter accumulated at the bottom of the swamps, gradually turning into peat and then, under pressure from new sediments, into coal. We burn this coal today. Every time a coal power plant operates, it releases the energy of sunlight captured by plants 300 million years ago. The carbon dioxide those plants once removed from the atmosphere returns again. In essence, we are undoing the work of the Carboniferous forests, and the consequences for the climate are becoming increasingly evident. In the Carboniferous, the first reptiles appeared, animals that finally broke their dependence on water. Their eggs, covered with a sturdy shell, could develop on land. This allowed reptiles to colonize the interior regions of the continents, inaccessible to amphibians. Reptiles were small, similar to modern lizards, but their descendants would become the rulers of the planet. The Carboniferous ended about 299 million years ago and was followed by the Permian period. The climate began to change. The supercontinent Pangaea, which united almost all Earth's land, created conditions for vast deserts in its interior. The humid, swampy forests retreated, giving way to more arid ecosystems. In the Permian, a new group of animals rose to prominence: the synapsids, ancestors of modern mammals. Do not confuse them with dinosaurs. Synapsids were an earlier and entirely separate evolutionary line. Some reached the size of a rhinoceros. Dimetrodon, with its famous sail on its back, is one of the most well-known representatives. Other synapsids were wolf-sized predators, and others were herbivores resembling pigs. By the end of the Permian, synapsids had become the dominant land vertebrates. It seemed that they were destined to rule the planet in the future. But fate decided otherwise. 252 million years ago, the greatest catastrophe in the history of life on Earth occurred: the Great Permian Extinction. About 95% of marine species and 70% of terrestrial species vanished forever. It was so devastating that life needed millions of years to recover its former diversity. The cause of the catastrophe was the Siberian traps, colossal volcanic eruptions covering an area the size of Western Europe. Lava poured from fissures in the crust for hundreds of thousands of years, releasing enormous amounts of carbon dioxide, sulfur compounds, and other gases into the atmosphere. The consequences were catastrophic. At first, sulfur aerosols caused short-term cooling, killing many species adapted to warm climates. Then the buildup of carbon dioxide led to global warming. Temperatures rose by 10 degrees or more. The oceans warmed and lost oxygen. Vast regions became dead zones. Almost nothing could survive there. On land, heat and drought turned huge territories into lifeless deserts. Life teetered on the brink of total annihilation, but survived. In some corners of the planet, conditions remained tolerable. Small populations of organisms clung to existence, waiting for better times. And when volcanic activity finally subsided and the climate began to stabilize, these survivors started to repopulate the empty world. The Triassic period, which followed the Great Extinction, was a time of recovery and restructuring. Ecological niches vacated by extinct species were gradually filled by new ones. And among these new rulers of the planet were creatures destined to shape Earth's appearance for the next 150 million years, the dinosaurs. The first dinosaurs appeared about 240 million years ago. They were small, about the size of a dog or slightly larger. They were not dominant. In the early Triassic, the land still belonged to surviving synapsids and various reptiles. But dinosaurs had advantages that eventually ensured their supremacy. One major advantage was their posture. Unlike most reptiles, whose limbs extend sideways, dinosaurs held their legs directly under their bodies. This made them more efficient movers, capable of greater speed and supporting more weight. Another advantage was probable warm-bloodedness, at least in some groups. Warm-blooded animals are active at any time of day and at almost any temperature, giving them an edge over cold-blooded competitors. By the end of the Triassic, dinosaurs had become a noticeable part of the fauna, but they still did not dominate. This changed after another mass extinction, the Triassic-Jurassic extinction, which occurred about 201 million years ago. It was less catastrophic than the Permian event, but it wiped out many of the dinosaurs' competitors. The path to dominance was open. The Jurassic period was the golden age of dinosaurs. The climate was warm and humid, and sea levels were high. Pangea began to break apart, creating new coastlines and marine corridors. Dinosaurs spread across all continents and occupied nearly every ecological niche. Among them were colossal sauropods, long-necked herbivorous giants, the largest animals ever to walk the earth. Diplodocus reached 25 meters in length. Brachiosaurus weighed more than 50 tons and could lift its head as high as a 5-story building. How could such animals exist? How did their hearts pump blood to such heights? How did they find enough food? Scientists are still searching for answers to these questions. But there were predators as well. Allosaurus, a 9-meter-long killer with sharp claws and teeth. Ceratosaurus with a horn on its nose. Megalosaurus, the first dinosaur ever given a scientific description back in 1824. These predators hunted herbivores, including young sauropods. But adult giants were likely too much for them. The difference in size was simply too great. The Jurassic period also saw the appearance of the first birds. Archaeopteryx, discovered in Germany, had feathers like modern birds, but also teeth and a bony tail like dinosaurs. It was a perfect transitional form, confirming the evolutionary connection between dinosaurs and birds. Today we know that birds are not just descendants of dinosaurs. They are dinosaurs, the only group that survived the mass extinction at the end of the Mesozoic era. The Cretaceous period, which replaced the Jurassic around 145 million years ago, became the time of the greatest dinosaur diversity. The famous ceratopsians appeared, horned dinosaurs such as Triceratops with its 3 horns and bony frill. Duck-billed hadrosaurs formed huge herds that roamed the plains. Ankylosaurs turned into living tanks, covered with bony armor and armed with clubs on their tails. And of course, Tyrannosaurus, the king of the dinosaurs. This predator appeared relatively late, about 68 million years ago, shortly before the end of the age of dinosaurs. But it managed to become one of the most formidable predators in the planet's history. 12 meters long, 6 tons in weight, with jaws capable of crushing bones. The bite of a Tyrannosaurus was the strongest of any land animal. But the Cretaceous was not only the age of dinosaurs. It was the time when flowering plants, angiosperms, flourished. These plants, with their bright flowers and nutritious fruits, revolutionized terrestrial ecosystems. They formed a symbiosis with pollinating insects, creating one of the most successful partnerships in the history of life. Bees, butterflies, beetles. All of them appeared or reached their peak thanks to flowering plants. In the seas of the Cretaceous, dinosaurs were not the rulers, other reptiles were. Mosasaurs, giant marine lizards up to 17 meters long. Plesiosaurs with their long necks and powerful flippers. Huge sea turtles the size of a car. Sharks continued their dominance, which had begun back in the Devonian. On land, small mammals hid in the shadow of the dinosaurs. They were tiny, mostly nocturnal, resembling modern shrews or possums. They had existed for more than 100 million years, but could not compete with dinosaurs for dominant ecological niches. They were waiting for their moment. And that moment came 66 million years ago, on the day that changed everything. In what is now the Gulf of Mexico, near the Yucatan Peninsula, an ordinary Cretaceous noon reigned. Pterosaurs glided over the waves. Mosasaurs hunted fish. On the shore, dinosaurs went about their daily routines, searching for food, caring for their young, escaping predators. None of them saw death approaching from space. An asteroid about 10 kilometers wide was rushing toward Earth at 20 kilometers per second. 1 second before impact, it was still in the stratosphere. The next second, it crashed into a shallow sea, broke through the Earth's crust, and released energy equivalent to billions of atomic bombs. At the point of impact, cubic kilometers of water and rock instantly vaporized. A shock wave spread at the speed of sound, sweeping away everything in its path. Within a 1,000-kilometer radius, all life died in the first minutes. But that was only the beginning. White-hot fragments of rock were thrown into space. They spread across the entire globe and began falling back, entering the atmosphere as meteors. The sky glowed. Air temperatures rose to levels at which forests ignited. Wildfires erupted across the planet. Smoke and ash rose into the atmosphere, blocking the sun. Then came darkness. Sunlight could not penetrate the veil of dust and soot. Photosynthesis stopped. Plants died without light. After them, the herbivores died, and then the predators that had lost their prey. Temperatures dropped. First because sunlight was blocked, then when the dust settled, warming began due to greenhouse gases released by the impact. The mass extinction at the end of the Cretaceous wiped out about 75% of all species on the planet. All non-avian Dinosaur vanished. Pterosaurs disappeared. Marine reptiles disappeared. Ammonites, which had thrived for hundreds of millions of years, were gone forever. But life, as always, found a way to survive. Small animals able to hide underground or in water endured the catastrophe. Plant seeds waited for the return of sunlight. Birds, the last dinosaurs, endured. And when the dust settled, when the sky cleared again, new actors stepped onto the emptied stage, the mammals. The first 10 million years after the extinction of dinosaurs, the Paleocene, were a time of experimentation. Mammals, freed from competition with dinosaurs, began rapidly increasing in size and occupying new niches. But they still did not resemble modern ones. Strange, peculiar forms filled the ecosystems, creatures that today seem almost as alien as dinosaurs. The Eocene, which began 56 million years ago, became the time when modern groups of mammals emerged. The first true horses appeared, small, dog-sized, with several toes on each foot. The ancestors of whales appeared, strange four-legged creatures that gradually returned to the sea. The first primates appeared, our distant ancestors climbing through the trees in the tropical forest that covered most of the land at the time. The Eocene climate was hot. Even beyond the Arctic Circle, palms and magnolias grew. Crocodiles lived in the Arctic. Sea levels were much higher than today. It was a world without ice, no polar ice caps, no mountain glaciers. But gradually, the climate began to change. Around 34 million years ago, a sharp cooling occurred. Antarctica, having separated from other continents, became isolated by a cold circumpolar current. Glaciers began to form on it. This event, the boundary between the Eocene and Oligocene, marked the transition to the modern Ice Age world. Tropical forests retreated, giving way to savannas and grasslands. Grasses, a relatively recent evolutionary innovation, began to dominate vast areas. Animals adapted to the new conditions. Horses, once forest dwellers, moved into open spaces. Their teeth grew taller to grind tough grass. Their legs grew longer to escape predators more quickly. The number of toes decreased. Modern horses stand on a single toe. About 23 million years ago began the Miocene, an era when mammals reached their greatest diversity. Herds of elephants with 4 tusks roamed the African savannas. Giant rhinoceroses, larger than modern elephants, lived in Asia. Bear dogs hunted on the plains of North America. It was a strange world, yet already recognizable. And somewhere in Africa, among forests and woodlands, lived apes. Small, 4-legged, not particularly remarkable compared to other primates of the time. But their descendants were destined to walk an astonishing path. Around 7 to 6 million years ago, important ecological changes took place in Africa. Forests continued to shrink, giving way to open savannas. Some apes faced a choice: retreat with the forests or adapt to the new environment. The ancestors of humans chose the second path. We do not know exactly who our last common ancestor with chimpanzees was. The fossil record of that period is scarce. But gradually, over millions of years, our ancestors became increasingly adapted to life in open landscapes. The first and most important change was the transition to bipedalism. Around 4.5 million years ago, Ardipithecus ramidus, walked the savannas of East Africa. She still resembled an ape in many ways. A small brain, long arms for climbing trees. But she could already walk on 2 legs, though awkwardly. A million years later came Lucy, the famous skeleton of Australopithecus afarensis, found in Ethiopia. Lucy was fully bipedal. Her pelvis and spine were adapted for upright walking. But her brain was still small, about 400 cubic centimeters, like that of a modern chimpanzee. Why did our ancestors need bipedalism? Many hypotheses exist. Perhaps it allowed them to better spot predators in tall grass. Perhaps it freed their hands for carrying food or infants. Perhaps it helped save energy during long journeys across the savanna. Most likely, all these factors played a role. But bipedalism had an unexpected consequence. Freed hands could be used for other purposes, for example, manipulating objects. And around 2.5 million years ago, our ancestors began making the first stone tools. These tools were primitive, just stones with chipped edges creating a cutting surface. But they opened a new world of possibilities. They allowed early humans to butcher animal carcasses, obtaining calorie-rich meat. They could crack bones to extract nutritious bone marrow. Meat and bone marrow are rich sources of protein and fat, essential for brain growth. And the brain began to grow. Homo habilis, who lived about 2 million years ago, had a brain volume of around 600 cubic centimeters, 1.5 times larger than that of Australopithecines. Homo erectus, who appeared around 2 million years ago, had a brain of about 900 cubic centimeters, and in later representatives, more than 1,000. Homo erectus was a true breakthrough. It was the first human species to leave Africa. About 1,800,000 years ago, Homo erectus began to spread across Eurasia. Its traces have been found in Georgia, China, and Indonesia. It mastered the use of fire, possibly the first of our ancestors to do so. Fire provided warmth, protection from predators, and the ability to cook food. Cooking was another revolution. Heat treatment makes food more digestible, allowing more calories to be extracted. This reduced the strain on the digestive system, which could become smaller and simpler. The freed energy was directed towards supporting the growing brain. For the next million years, Homo erectus and its descendants continued to evolve. Different populations formed in different regions. In Europe appeared the Neanderthals, Homo neanderthalensis. They were stocky, muscular, with large noses, the perfect build for the cold glacial climate. Their brains were even larger than those of modern humans. In Asia lived the Dinosaurs, a mysterious group known mostly from DNA extracted from a few bones and teeth. On the Indonesian island of Flores lived the dwarf humans, Homo floresiensis, only about a meter tall, with small brains, but capable of making stone tools. And somewhere in Africa, about 300,000 years ago, our species appeared, Homo sapiens, the wise human. The earliest Homo sapiens did not differ greatly from their contemporaries, Neanderthals and Denisovans. They had the same brain volume, similar tools, and similar lifestyles. What made us special? Some scientists point to language. Perhaps Homo sapiens developed more complex speech, allowing them to transmit abstract ideas, plan for the future, and teach their offspring. Others emphasize sociality, the ability to form large groups united by shared beliefs and stories. Around 70,000 years ago, something changed. Homo sapiens began creating symbolic artifacts, ornaments, ritual burials, cave paintings. This indicates the emergence of symbolic thinking, the ability to use one thing to represent another. The letter you are reading right now is a symbol. A word is a symbol. Money is a symbol. Our civilization is built on symbols. Around the same time, Homo sapiens began a second wave of migration out of Africa. The first attempt, around 100,000 years ago, was not successful. Those migrants left no descendants among modern humans. But 70,000 years ago, a small group of our ancestors left Africa and gave rise to all non-African humanity. They moved quickly, faster than any previous hominid migrations. Over several tens of thousands of years, Homo sapiens settled all of Eurasia, reached Australia, and later the Americas. Everywhere they arrived, other human species disappeared. Neanderthals went extinct about 40,000 years ago. Denisovans around the same time. Homo floresiensis survived longer, but also vanished. Was this due to direct extermination, competition for resources, or absorption through interbreeding? We don't know exactly. Likely all these factors played a role. We know that interbreeding occurred. In the genomes of modern people of non-African origin, there is between 1 and 4% Neanderthal DNA. Some Asian and Oceanian populations also carry Denisovan DNA. About 12,000 years ago, the last ice age ended. Massive glaciers covering North America and Northern Europe began to melt. Sea levels rose by more than 100 meters. The climate warmed and stabilized. The Holocene epoch began, our time. And it was in the Holocene that the last great revolution occurred, the Neolithic one. Humans transitioned from hunting and gathering to agriculture and animal husbandry. This happened independently in several regions of the world, in the Fertile Crescent of the Middle East, in the valleys of Chinese rivers, in Mesoamerica, and in the Andes. Why did it happen then? Partly because of climate change. The stable and warm climate of the Holocene created conditions favorable for agriculture. Partly because of population growth, which made the traditional hunter-gatherer lifestyle increasingly unsustainable. Agriculture changed everything. It allowed for the production of surplus food that could be stored. This freed part of the population from the need to obtain food. They could engage in crafts, administration, war. Permanent settlements appeared, then towns. Writing emerged, necessary for record-keeping and managing complex economies. States appeared with their armies, laws, and bureaucracies. Over the last 10,000 years, humanity has traveled a path from the first villages to a global civilization. We built pyramids and skyscrapers, invented the wheel and spacecraft, wrote epics, and deciphered the genetic code. We became a geological force reshaping the face of the planet. And all this in 4 seconds, if all of Earth's history were compressed into a single day. Look around you. Everything you see is the result of 4.5 billion years of evolution. Every atom in your body was forged in stars that exploded long before the solar system formed. Every cell in your body is a descendant of the first living cell that appeared in the ancient ocean 4 billion years ago. You carry the heritage of trillions of ancestors, from bacteria to fish, from reptiles to apes. You are a part of an unbroken chain of life stretching across the abyss of time. And that chain does not end with you. It continues in your children, in their children, and so on, into a future we cannot even imagine. The Earth existed for 4.5 billion years before us. It will exist for billions of years after us, until the sun becomes a red giant and engulfs it. We are only a moment in its history, but this moment belongs to us. Will we use it wisely? That depends on us. We have traveled the path from molecules to mind, from chaos to civilization. We learned to understand the laws of nature and harness the energy of the atom. We sent messages to the stars and took our first steps into space. But we have also created weapons capable of destroying our civilization and altered the planet's climate with consequences that will be felt for thousands of years. Earth's history teaches us that life is astonishingly resilient. It survived a collision with another planet, global ice ages, mass extinctions. But it also teaches us that individual species, even the most successful, can disappear forever. Dinosaurs ruled the planet for 150 million years, but their era ended in a single day. We have existed as a species for 300,000 years. Our civilization, about 10,000. Our industrial era, about 200. We are incredibly young by geological standards, but we have already become a force capable of changing the planet faster than asteroids and volcanoes. What awaits us in the future? Will we be the first species to consciously guide its own evolution and the fate of its planet? Or will we become just another layer in the geological record? An interesting but brief episode in Earth's history? The answer to that question will be written by us. With every decision, every action, because we are not just the product of 4.5 billion years of evolution. We are its consciousness. We are the way the universe becomes aware of itself. And this journey to the beginning of time is only the first step to understanding who we are and where we are going.